Alright guys, properties of logarithms. So to begin with, you have to get comfortable with your properties of exponents. So realize that whenever you are multiplying the bases, that's the same thing as adding the two exponents, saying how many x's do I have? Division, likewise, we're used to seeing it as x to the a over x to the b. It's when you are subtracting your exponents. And a power to a power, it's like distributive property, you always multiply across the parentheses. Now, a really important property, especially going in this direction, is rewriting a log as an exponential or an exponential as a log. So here's the base that the log is sitting on. So here's your base, and then the exponent, that unknown exponent, that's what we're trying to solve for. So it's really important to be able to be comfortable going back and forth when you are solving log problems. So now we have the actual properties of our log. So notice that you have a product of your argument becomes the addition. So this is expanding it. Again, it's really important to go backwards and to be able to condense these, and that's what you're going to do when you are solving a log problem. Same for when you have the subtraction, it becomes division. And this is a huge property, again going backwards, where when you have a coefficient, that coefficient can go upstairs as a power, or the power can come downstairs as a coefficient. But we use this when we're trying to simplify or solve a problem. Now, to show some of the properties that are most common and help in simplifying your logs, these are based on rewriting it as an exponential. We know that b to the 0, anything to the 0 power, equals 1. We know that a base raised to the 1 is going to equal itself. And here, based on what we just did, if the log base b of b is basically itself is 1, this would cancel to 1 and you get x equals x, a nice identity. And then you have the change of base property. Change of base is important if you're trying to evaluate it on your calculator. Usually our base c, that's the default base, is base 10, but sometimes you just want to put it into a different base so that it matches. So this is how you would do it. Notice the bigger number goes upstairs and the base, which is a little bit lower, goes downstairs, and you can change it to whatever base you want. So now we have some basic strategies, and I'm going to actually work these problems out on the next page, but notice what these strategies are. We want to, sometimes if we can, try and write them as the same base. Both of these can be rewritten with a base of 2, and even though they look like they are related, if you can't write it with the same base, like 6 and 12 do not have the same exponential base, then you have to take the log or the natural log of both sides. Then you're also looking, do you have logs on both sides of the equal signs? Now this is not a balanced log. We're going to have to use our properties to condense this. Then I have a log equals a log. That is going to always be your goal with those problems. And then this next one, we have a log and then a number. So again, we will have to use our properties to condense this. And when you get a log equals a number, what you want to do is write it as an exponential. And then, of course, we have our natural log and our e problems, which are the same strategies, but using your natural logarithm. And then we have our word problems, exponential, growth, and decay. You will be given which problem to deal with, but just as a reminder, a or y, the number that's isolated on the other side of the equal sign always represent the amount after a certain amount of time has passed. But you have the number right up against your exponential. That is your initial deposit. That's the amount of money that you first put into the bank, or that is the amount of substance that is initially present at t equals 0. Then you have a rate of growth or a rate of decay, depending on what they give you. And of course, t is always time. Okay, so now let's work out some of these logarithm problems that were on the other page. So we start off with 4 to the x equals 8 to the 2x plus 1. And as we said, we can rewrite both of these with a base of 2. So this would be 2 to the 2x equals 2 cubed. And then we have to put the exponent that already sits there in parentheses, because that 3 will have to distribute. But once you do that, I can now get rid of these 2's, and I'm only having to solve 2x equals 6x plus 3. So that makes it a much nicer problem, and we can subtract 6x equals 3, so we get that x equals a negative 3/4. Okay, so that was the first problem. It's nice if you can write them with the same base, but as we said, that's not always possible. So when we had 6x equals 12 to the x plus 1, even though they look like they're related, they do not have the same base. So I'm going to take the natural log of both sides. Now these problems are going to get a little bit ugly, and the reason why you take the natural log is so you can move that exponent down in front. So I have x ln of 6 equals, in parentheses, x plus 1 ln of 12. So remember, ln of 6 and ln of 12 are just numbers. So what I'm going to do is I'm going to take those two decimal numbers and I'm going to put them together so I don't have decimals everywhere. So if you do it on your calculator, ln of 6 over ln of 12 is about 0.72. That's going to now equal x plus 1. So I have 0.72x minus x equals 1. So that's going to be negative 0.28x equals 1. So solving for x, we get it to be negative 1 over 0.28, which is about negative 3.57. So those problems will involve using a calculator and getting decimal approximations. Now we have our logs that we want to create a balanced log, because we have logs on both sides. So we're going to be utilizing our properties to condense our double log on the one side. So since it's addition, we know that it's going to be 2 times 7, which is 14, and that equals log base 3 x plus 3. Once you have that, it's kind of like having same bases. You can cancel those out and it just becomes 14 equals x plus 3. So x is going to equal a very friendly 11. Okay, so now let's move and do our log x plus log x plus 3 equals 1. Now notice there's not even any base written, so you want to recognize that when there's nothing written, it's understood that that's going to be a base 10. So we need to use our properties to make this into one log base 10. So since it's addition, that'll become multiplication, x squared plus 3x equals 1. And here's where you have a log equals a number. So this is your base, and this is your exponent. We're going to rewrite it as an exponential. 10 to the 1 equals x squared plus 3x. And you should recognize that as a quadratic. So x squared plus 3x minus 10. And we go ahead and factor. So this is x plus 5, x minus 2 equals 0. So x equals a negative 5 or a positive 2. We have to throw out the negative because it would have made one of my arguments, actually both of my arguments, negative, and that's not allowed. So you only have the one answer. Then we get on to our natural log problems. So we have ln of x plus 2 equals 4. Remember that natural log is just another way of saying log base e. So it's just like this problem we just did. You have a log equals a number, so we're going to write it as an exponential. So the log goes away, and this becomes e to the 4th. And so we have x equals e to the 4th minus 2. And if you want, you can plug that in your calculator or leave it as an exact answer. And then the last one, we have 4e to the 2x equals 8. Now we're so used to saying you're going to natural log both sides, but be warned, you have to isolate your exponential first. So dividing by 4, I have e to the 2x equals 2. Now I can go ahead and take the natural log of both sides. So these will cancel. 2 to the x equals ln of 2. So x equals ln of 2 divided by 2. And that should give you a pretty good feel for how these kind of problems are going to work out.